Bonjour.
Hi.
Hello. Good. All right. So, وقت حنعمل يفوت بعد شوف. Alright, so we can start. Okay, so basically, what we saw last time is the Euler method, and we saw how we can derive more accurate methods using second Taylor order expansion or higher integration, higher order integration method like the trapezoidal integration.
في تلاميذ بعد ما فوتتم.
Sorry, بعد في تلاميذ yeah. Okay, so now we are going to talk about the Range-Kutta methods. So the Range-Kutta methods are explicit methods. Okay? Explicit methods, I repeat, means that we can directly calculate the solution at time I plus 1 from the solution at time I, or the solution at time I from the solution at time I minus 1 instead. So the Range-Kutta methods are the most used explicit methods. And especially the Range-Kutta 4, the Range-Kutta Okay, A and B. So the RK2A consists of finding the points here yi plus 1 from the point yi using the following formula. I will show you after how these methods are derived. Okay, plus h f of xi plus h over 2, okay, yi plus h over 2 f of xi yi. So here, right, so this is in front of all this. The other was yi plus h of xi yi. Here it's yi plus h of xi plus h over 2 yi plus h over 2 f of xi yi. Right? So this is the x part and this is the y part. All right. So now for the RK2B, right? For the RK2B, the points yi plus 1 is evaluated the following: yi plus h over 2 f of xi yi, okay, plus f of x I plus 1, okay, h of f of x I y, sorry, yi plus a. Okay, plus h here. Okay. So it's h over 2, okay, the sum of f of x I y I plus f of x I plus 1 yi plus h of x I y I, right? So I will show you how these methods are derived, okay? But before that, okay, there's equivalent formulation, okay, which makes these things easier to, I mean, to formulate or to learn, right? If you want to learn it, but I prefer that you derive the methods. I will show you how the methods are derived quite simply. Okay, so for the RK2A, you can define the quantity K1 is equal h of f of xi yi. Okay, the quantity K2, which is h of um, f of xi plus h over 2 yi plus k1 over 2. Okay, k1 is this quantity here. And then yi plus 1 being here yi plus k2. And for the RK4, sorry, RK2B, we have K1 is equal to h of f of xi yi, okay, the same thing. And K2 is equal h of xi plus h instead of plus h over 2. It's yi plus k1. Okay, and then yi plus 1 is yi plus half k1 plus k2. Okay, so this is the same thing than this expression. Right? It's the same thing, but it's maybe easier, I mean, to learn this than this. Right? Now, let's see for the derivation of the RK2A and RK2B. Okay, so let's start by the derivation of the RK2A. Okay, so the RK2A is derived from the midpoint rectangle approximation. Okay, can be derived from the rectangle. So basically, if we consider, I told you that the right, so y prime, the problem that we have is y prime of x is equal to f of x, y. This problem is equivalent, okay, to, okay, yi plus 1. So if we take the integral, we get that yi plus 1 is yi plus the integral from xi to xi plus 1, okay, of f of t, y of t, dt, where t is the other binary here, okay. So in case of the Euler, the integral here is replaced by h, okay, f of xi for the left corner approximation. Of course, if you use the right corner approximation, you will get h of f of xi plus 1, but this will be an implicit method, right? It will not be an explicit method. Now, here, if you use the midpoint, okay, now if you use the midpoint for this, what would it be? Somebody?
midpoint rectangle يعني.
Right. So for the left corner, it was h f of xi yi. That's good because you take the left corner only here. If you approximate by one rectangle, this thing. Okay. If it's the midpoint, you take h multiplied by f of what?
Over 2 يعني نصها.
Yeah, it's yi plus h f of xi plus h over 2. Okay. Y of xi plus h over 2, right?
Okay. Okay.
Now here, this thing we need to express it in function of xi, but because we don't have the y of xi plus h over 2. Now here we can use the Taylor approximation. So y of xi plus h over 2, right, is equal, I'll put like this, right, y of xi plus h over 2, okay, y prime of xi, y prime at the point xi plus higher order term, but y prime at the point xi, y prime is f of xi yi, right? So you have y of xi plus h over 2 f of xi squared. And now when you replace this in here, you get the RK2A. So yi plus 1 is equal to yi plus your h, okay, of f of xi plus h over 2. Now replace this, okay, here, which you have the term that we neglect. Replace this by this expression, right? The y of xi plus h over 2 by y of xi and yi plus h over 2 f of xi y. Okay? So this is yi is equal to, okay, it's h f of xi plus h over 2 yi plus h over 2 f of xi. So this is the RK2A, okay? So this is the expression here, okay? It's obtained from the midpoint rectangle approximation. And this is more accurate than the left corner here. Now, for just 2 points, the midpoint is more accurate because, you know, like if you have, for example, something like this, and you take the rectangle here, right? So the area of this, so you see here, okay, this is superior, this is inferior, but this here you take like the middle of the both, right? So, and if you would take this rectangle here, okay, sorry, this rectangle, it's inferior, and if you take this rectangle here, it would be superior, right? So here you're taking the midpoint. So for just 2 points, the midpoint rectangle is more, it's more accurate. Right? So this is a second order method. So we can prove that it's second order method. Okay, although, you know, in this approximation we retain just the first order, then the Taylor approximation, okay, it's still here, okay, more accurate than the other. Okay. Now the RK2B. Hello, اسمعوني؟ Hello?
Yes, yes.
Yeah, okay. Now the RK2B is derived from the trapezoid integration. Right, so basically you have that y of I plus 1, yani y of xi plus h. Okay. Okay, like I said, it's y of xi and yi plus the integral from xi to xi plus 1. Okay, f of 2 y of t. Right. Now, if you replace this by the trapezoid, what we get? Just the trapezoid between xi and using the points xi and xi plus 1. What do we get?
H over 2 times
Yeah.
f of xi yi
Yes.
plus f
Yeah.
of xi plus h y plus h
Yeah.
معاك
يعني xi plus h يعني xi plus 1 here.
xi plus
Okay, y plus 1. Okay, this is xi plus h and I plus 1. Okay. Okay. Now, this quantity here, we don't have it. This is, as we said, this is an implicit method because, see, you need to solve a nonlinear equation here in y plus 1 to get the solution. Now, trick here is to express here now yi plus 1. If you take the first order Taylor development, you use the formula of the Euler here inside of this. Okay, so this is equal to yi. Okay, y of xi plus h is equal to y of xi plus h. Okay, y prime at the point xi in okay f of xi yi plus higher order. Right? It's yi plus h f of xi y. This is here the Euler expression, but we use it for this point here. So, right. So here, what you get now the RK2. You replace now this here y plus 1. You replace it by this quantity, and then you get here y of xi is equal plus h over 2 f of xi yi plus f of xi plus 1 and xi plus h. Okay, xi plus 1. Okay, yi plus h f of xi. Use the parentheses in front of this. Okay. So this is the expression that we get here. Right, so it's the RK2. Correct?
okay
So because it's an implicit method here, we use a trick to express this y plus 1. So, okay, so basically the Euler, so it's a first order method. These are second order methods. Okay, yani the equivalent to second order Taylor expansion, because we saw that the trapezoidal integration correspond to a second order method. Now, if we want even better, we need to use the fourth order Range-Kutta method. Okay, or RK4, Range-Kutta method of order 4. Now, this method, okay, so if we need more accurate methods and we want to derive it from the integration, what we must use? What's the most accurate integration method?
was it the trapezoid ما بعرف
لا بعد الترابيزويد عملنا واحدة.
شو كان اسمها
The Simpson, right?
Simpson
The Simpson, which is based on the Lagrange polynomial.
yes
right?
yes
So the RK4 is derived from the Simpson integration. Okay.
okay
Now there is other methods كمان to derive these Range-Kutta methods. إذا بدكم فينا أعطيكم PDF how to derive other from the integration, right? But now I will not derive the RK4, okay, because the derivation is a little bit long, but I will give you like the expression of the RK4. So the RK4, so as we defined here, for example, K1, K2, okay, the expression of the RK4 is quite long. So to express it in a way like this, it's quite long. We'll express it, okay, by using variable of this. So RK4 is, we define K1 as being h of xi, yi. K2 as being h of xi plus h over 2 yi plus k1 over 2. Okay. So until now, if you see, it's the same thing that RK2A. Okay. It's the same thing until now. K3 as being h of x I plus h over 2 yi plus k2 over 2, okay, k2 that we just derived now, k4 h of xi plus h yi plus k2. And then you get yi plus 1 is equal to yi plus 1 over 6, okay. K1 plus 2k2 plus 2k3 plus k4. So the IK4 is so based on the Simpson integration. So if you have okay, integration of the function f of xi yi, okay, but here you integrate it, okay. So if you have the point xi plus h, okay, but also you take the point here xi plus h over 2, and you construct the interpolation polynomial here, okay, and you use the Simpson integration for this here. Okay. That's good. Okay. Maybe I will see if I can send you the I can do derivation and send you by PDF, right? Now there's other way to derive other than the integration, okay? So you can derive these methods using the Taylor expansion, okay? So the RK4 is a force order method. It's the most accurate. Okay. So force order method, yani it's equivalent to a force order Taylor expansion. Okay, yani retaining the fourth order and neglecting the fifth order of the Taylor expansion. Okay, but as you can see, the explicit method, they always calculate, okay, the points yi plus 1 from the point yi, okay, using different formula, and according to the formulas, you get a result that is more or less accurate. Did somebody solve the program?
Yes, I did.
I want
وبعت لك yeah.
انت بعت لي اوكي مش اوكي اذا بدكم بعد فيني اعطيكم مجال يعني انه to solve it. We will solve now some exercise. عندكم شيء بعدين؟ على 3؟
لا ما بعتقد.
Okay, let's show you the programs then. Yes, it's okay. Um, please. Just waiting. My computer to recognize my hard disk and it's not related. Right, not it. All right, so share the screen. PC is a little bit slow, so it's taking 1 hour to open the MATLAB. Right.
دكتور نحن بعد عنا تشابتر واحد.
Yeah. Right, so فينا نزيد séance one lecture next week so we can accelerate.
Finish it. Okay.
I don't know how much we'll finish next week because it's a long chapter, but the faster we finish is better. So, all right, so okay, so you see the function that is called Euler. Now you don't need to define a function, but I define the function so I can after call them. So this function Euler returns the vector y of same size of the vectors x as input, where the vector x is the input and the y1, the initial solution, is the input. So n is equal to length of x, okay, here, okay, and then y1 is equal, right, y of 1, the first point, is y1, the initial condition. H is equal to the step. Okay, we suppose that x is a vector that is of equal step, so it's the second point x2 minus x1. So any xi plus 1 minus xi must give you the same result here, right? So like I said, you don't need to write a function here, okay, but I wrote it as a function. So for I equals 1 till n minus 1, okay, y of I plus 1 is equal to yi plus h of xi yi. This is the only thing. This is the, right? So you make a loop, then you calculate the second point from the first point extra. Now you need to define the function f of xi yi, right? So here I will open the function. I'm sorry, subcat MATLAB. Okay. Yes. So we can continue. اسمعوني. Hello.
يس دكتور بسمع.
Okay. So this was the Euler. Okay. As you see the function here, f of. Okay. I'll put y here. So the function f here, it's the function f of x, y. Okay, it depends on your problem. So I will put here, okay, no, I will not choose here y, I will use r. Okay, so the result will be minus xy. So this function will return minus xy. All right, for now, I will save it here. And I will launch the Euler. And now here, okay, so I will, oh, yes. So I will define a new in the main. All right, so let's open the main. All right, so okay, comment now this for now. Okay, so this is my x min, yani x min is, okay, I will call it A and B because you're more used to A and B. So this is A, this is B, all right? This is the number of steps, right? So now I'll define this like this. So these are this is the number of sub-interval, right? So H is B minus A divided by M, right? And the X is the vector from A to B, right? With a step of H. عم تقشعوا؟
Yes.
Okay, so y1 is equal to 1, and now I will call the error, right? So it's error x y1, so I will call it. So y is equal to error, okay, x y1. This will return here the, okay, the vector y. As I said, you don't need here to write this into function. You can just like write this here, all right? Or even you have defined the h to just like, you can just like use this loop in the main, right? But I prefer to define a function so I can call all my functions easily, right? So, and now you can plot the xy and see what you get. And now I will plot with the xy. I know that the solution of with f is equal minus x multiplied by y. We solve this, okay, solution. And we know that this is equal to x minus exponential minus x squared over 2. So it's a Gaussian, okay. So I will plot the theoretical solution also, okay. I will plot this in points here, the calculated solution. And I will plot the theoretical solution here. And um, in blue. Okay. So here it's x1. Okay. So here it's in dots. I can put dot red if I want. Let's just like plot this and see what we get. So what it's saying here, there's a mistake. Okay, I'll call it something else than Euler because apparently Euler uh, Euler exists in MATLAB. So okay, so the function Euler exists in MATLAB. So I'll call it Euler A. So matter here.
Okay.
And we'll run it here. Well, I have to define this in Euler A. Say this. You have to define the name, the name of the file of the function as the name of the function. So, right. So now it works. So, okay. So do you see the graph or not?
لا.
Yes, let me show you. Okay, you see it? It's almost correct. I mean, in red is the calculated points. Okay, and in blue is the theoretical function exponential minus x squared over 2. Okay, so it's almost correct. Now, what happens? Okay, let's return now to the main here. And let's change the function f. Let's take this value. Okay, this problem we solved it also, and we showed that the solution of this was exponential minus x. Remember, when f of xy is 5y minus 6 exponential minus x, this we solved it in class, and the solution was exponential minus x. Okay, but the problem here, okay, is that the solution is very sensitive to initial round-off error. So we expect that we will have some problem here with the error, right? So I will just like plot and see. Now I have to compare with exponential minus x and not exponential, okay, minus x squared over 2, and see what happens here. See, right, so let's share the screen and show you what happens. Oh, you see, it started good, but then it's the error accumulates and the small mistake that you have in the beginning, okay, leads to a catastrophical error the more the x is large. Okay, so let's take till b equals 2, so you can see that now look how it changed, how the solution diverged from the right solution. It's like crazy. It goes.
Mm.
Okay, this is the calculated thing. Okay, the error increases and then it diverges completely from the solution. So the solution here is exponential, but because here it still didn't decrease enough. So this is on the scale of this, you know, this is much larger than this. That's why you don't see here the exponential. But if you take, for example, let's take b equals 1.5. Okay, let's see a bit better. So here, how it diverge. Okay, you see the figure?
Yes.
Yeah, you see how this is the exponential. This
Mm-hmm.
is the computed solution. Okay. Now, instead of Euler, let's take the RK2A or B. Okay. So I write a function that calculates the both. You know, like, but uh, like you're not obliged to do that neither. You can just like use the RK2A or the RK2B. So it's this one or this one. Right. So do you see the screen for the RK2AB?
Yes.
Okay. So it takes as input the vector x and the initial solution y1, and this is the same, right? So here I defined, so here this function returns the solution of the RK2A and the RK2B. But like I said, you can return one of the two if, and you're not obliged even to use a function if you don't want, okay? So this is the formulas for the RK2A and the RK2B. Okay, so RK2A, y of I plus 1 is equal to y of I plus h f of xi plus h over 2 y I plus, okay, h over 2 f of xi yi. And for the RK2B, it's yi plus h over 2 f of xi yi plus f of xi plus h y of I plus h over xi, y. Now, I just called the solution of the RK2A, I called it YA and here YB, just to differentiate between the two. Right? But if you're using one of the RK2A or RK2B, you can just like use Y, okay, here for the solution, and not necessarily YA and YB. It just is to differentiate between the two, okay, RK2A and RK2B. And like I said, if you want to calculate just the RK2A, for example, just comment this and you will have this, right? You just comment this and you return just like, okay, the YA, or you can call it Y if you want, okay? Okay, now let's, if we call the same thing, let's call the RK2A here, okay? And let's plot them together, okay, with the other. Okay, just like, hold on here. I will plot XYA and plot and dashed, and here the YB, let's plot it in circle, for example. Okay, okay, and the theoretical solution is already here. Let's compare. Right, so you can see that here for 1.5, this is the error.
We can't
RK2A,
see.
RK2B, I think, wait, just like, okay, this is, which one is, yeah, so this one is, this is the RK2A, right? RK2B, RK2A, almost the same thing. It's still close enough from the solution, but it diverges, you know, like for 1.5, it already diverged. If you take 2, okay, x equal 2, you will see that it diverged. The earlier had already diverged here completely from the solution, okay. For x equals 0, 5, all they are all already still acceptable here. For the RK2A and B, for x equals 1, it's still acceptable after it's diverging. If I increase B till 2 just to see how it looks like, you see that all the methods have already diverged from the solution. Okay, so they differ from the solution then here. Okay, but of course less than the Euler. So the Euler is the most catastrophic because it's first order. These are second order. They behave almost the same. Okay. Now the RK2A is a little bit better here, but it's not always the case. Okay, but they're almost the same. Okay, and here. Now let's see for the RK4. Now the RK4. Right. So let's show you the program. Okay, تعال تشوفوا الفيجر or not?
لا
الو؟
ما كانت مبينة.
طب لا ليه ما قلتوا لي؟ Okay, so you share. Where's the video? عم بحكي على الفاضي يعني.
لا فهمنا الدايفرجز شوي أقل من
So just
method.
okay, you see?
Yep.
Okay, see this is the alert. RK2B, RK2A here in dots.
Mm-hmm.
And this is the solution in the solid line.
Yep.
You see the difference. So the alert is the most catastrophical, and here, I mean, it's still close, but it's already diverged from the solution. Okay, now let's see for the RT4. And so the RT4, let's show you the first. Okay. You see something? Hello?
مبين
Any
شو
function
اسمه ساين
type?
ان. لا
No.
مبين انترنت.
Now,
هلا بين اوكي.
okay, so the same thing here, the beginning. And now for I equals 1 till n minus 1, right? Because here, in this case, n is the number of points, okay, it's the length of x. Okay. So you take a go to n minus 1 because here you're making I plus 1. So that's why you go to n minus 1 for all the functions. And here you calculate k1 h of xi yi, k2 is equal f of xi plus h over 2 plus k1 over 2, k3 is h of xi plus h over 2 yi plus k2 over 2, k4 is h of xi plus 1 yi plus k3, and then you get yi plus 1 is yi plus 1 over 6, okay, k1 plus 2 k2 plus 2 k3 plus k4. And this is the RK4, right? So it's supposed to be more accurate. Now let's call the RK4 and let's plot. Call it Y4 here. Okay, so I'm calling the RK4, and now we plot it in, I don't know, like triangles and so or something. Just to see x, y4. Okay, so I call the function RK4 here. Okay. I don't know if T gives me triangle, I think. Let's see. Okay, so let's put dot K. Okay, now let's show you the picture. Okay, you see that the RK4 is in the black dots. You see it? The theoretical solution is in blue here, this one. You see that it's still overlapping the theoretical solution here. Do you see the figure? Hello?
Yes, yes.
You see, it's still working the RK4 for x equal 2. Okay? So now I will just plot the RK4. Okay, I forgot about the rest and just like plot the RK4 with the other one. Okay, so you can better see because it changes scale when you plot with the other one because the error goes downs to negative a lot. So the exponential is not, I mean, it's condensed, compressed. So okay, so we will just like compare the two now, the RK4 and the right. Let's wait. It's exponential x. Right. Okay, you can see. Okay, I will share the screen. Okay. Okay, so you can see that in black dots is the RK4 and in blue is the theoretical solution. You see that it's still perfectly working the RK4 for x equal 2 and till x equals 2, it works perfectly. We saw that this problem, the error increases exponentially with x, okay? But still for x equal 2, it's working perfectly. Now let's increase till x, till b equals 3 here, right? Let's increase the b here. You see that for b equals 3, okay. You see that the problem starts here, okay? For 2, it's good, and then so this problem is by nature very hard to solve numerically because the error increases exponentially with x, and numerical methods induce error. And if you have error at a given step, the error will accumulate, right? And this type of problem, okay, with this f of xy, okay, we saw that the error increases exponentially with the error on the initial solution. So every numerical method has a limit for this type of problem. Okay, so the RK4 works good for, okay, till x equal 2, but after it's diverging. Okay, while the RK2A works for till x equals 1, the error till x equals 0.5, okay, inferior to 1, etc. But I mean, for the problem f of xy is equal minus xy, where the solution was a Gaussian, all the method work, okay? All the method will work, even the error, okay? Because here the error is not increasing exponentially with the variable x, okay?
No.
You can maybe try to write the programs in your way, okay, like these programs, and verify my sayings here, okay, corresponding the
Okay.
error, things like that. Okay, so we'll see you next week. Okay, I will send you some problems concerning this chapter. Okay, and if you have any
Okay.
questions, you can always ask, right, by WhatsApp or. Okay, and I will send you some
Okay.
problems. Try to solve it. I mean, it's very easy problems. Okay, like the examples that we saw in class, and it's this type of problems that you will have at the exam, and so try to solve it. We'll correct it next time. Okay,
Okay.
or I will send you the solution.
Mhm.
So and we still have one chapter concerning the system of linear equation.
Okay.
Okay.
All right.
Yeah. See you
خلص
next
next
time.
week
Thank
يعني
you.
Bye.
Bye.